All right, so let's now move on to refrigerators, air conditioners, and heat pumps. And we're going to see that we're going to switch things up this time from when we just talked about heat engines. And what we saw was that relating to the second law of thermodynamics, when we studied the heat engine, um, the heat was flowing spontaneously from the high temperature to the low temperature. And as it turns out, we can reverse everything if we apply work. And that's what we're going to be looking at with these heat transfers, because we want to take the heat from the cold reservoir this time around and dump that into our hot reservoir. So let's take a closer look. So in this picture, we have side to side the heat engine that we just studied and the refrigerator. And you can see that they actually look extremely similar. We just switched out the arrows. So now instead of having heat flowing from the hot reservoir into the engine, it's actually leaving the refrigerator and going into our hot reservoir. What is our hot reservoir in this case? It's going to be the room in which the refrigerator is, so typically your kitchen, okay? In order for this process to be reversed, you can see that now the work is not performed by the engine. It's actually, so where the work is actually being done to reverse the flow of heat. And the cold reservoir, which is actually the one that is interesting in this case, is the inside of the refrigerator. So we're pulling heat out of that and dumping it in the kitchen. And because we are going from, we're taking heat from the cold reservoir and then that's going into the hot reservoir. According to the second law of thermodynamics, we actually have to provide work to do so. So you can see that if we do the same kind of reasoning that we apply to the heat engine, we're going to have to change a few things here because everything runs backwards. So we use work to extract heat from the cold reservoir. So we take the heat from the inside of our fridge and then it goes out in the kitchen. So you can see that our equation that relates Q hot and Q cold in the work is going to look different. So um, the heat that is exhausted to the kitchen is going to be more than the heat that's removed from the refrigerator. That's important because it means that you um, will see that this is important, especially when we're going to apply that to the air conditioning system in just a second. So, but just take a note of that. So the heat that is exhausted to the kitchen. So again, if you look at this diagram, this would be the QH. It's QC plus the work. Okay, so you can see that we take QC plus the amount of work that is done. Okay, so if we look at the efficiency, right? So for the heat engine, we're looking at the work that was performed, which was what we wanted to maximize. In this case, that's definitely not the case. In this case, we actually want to take as much heat as possible from the cold reservoir. So that's our QC. And we want to do so with as little work as possible. So it's QC over W. And this is actually called a coefficient of performance. And so unlike the efficiency, it's actually a number that is not less than 1. And typically values for your typical refrigerators are going to be between 2 and 6. And you want, once again, to have this be as large as possible. All right, so air conditioning, it's the same as the refrigerator. What we're changing is what the hot and cold reservoirs are going to be. So in this case, the cold reservoir is going to be the inside of your room or of your house. That's what we want to keep cold. So we're going to extract heat from that reservoir. It's going to require work, so that's why it's plugged in, and we need that energy, that external source of energy. And then we take that excess heat and we dump it outside. Okay. So what is interesting, and because if we apply this equation again, you can see that the heat that is exhausted to the outside is greater than the heat that's removed from the cold reservoir. So this is why when you're setting up your air conditioner, you have to be very careful and make sure that you have an exhaust that goes to the outside and not inside of your house, because what would end up happening is that if you just turned on the air conditioning, it would absorb some heat from your room, but it would exhaust more heat, so you'd end up actually warming up the inside of your house. So it's very important that you actually dump that into the outside. Otherwise, you're actually warming up your home. And it's the same reason. So if you want to keep the door of the refrigerator closed, and otherwise you have the same type of issue, because um, if you keep the refrigerator door open, and in the end, so you're absorbing heat, but now it's one big room, right? And so you don't have the closed container. You end up essentially just warming up your kitchen if you were to do that, because you are absorbing heat, but then you're dumping more out. And that's because we need to include the work that is being added, that has to be going somewhere. And so if we're not careful, we may end up with the exact opposite of what we're trying to do. Okay. If we look at a heat pump, and so it's a similar idea, but this time you reverse the hot and cold reservoirs. So you can see that in that case, the cold reservoir is going to be the outside. The hot reservoir is the inside. So we want heat to come in this time. So we um, take heat from the cold reservoir, so outside, and then we dump it into the inside of the house to keep it warm. And again, because we're reversing the process, we're going from cold to hot, we have to produce work. And in this case, what is interesting though is that the work that is being added, so the work that the pump is needed to perform this process, actually does contribute. So it is warming up the house, which is what we're looking for. Um, so this is all good, but we still have to connect to the outside to be able to get that heat from the outside. So for a heat pump, again, we have to be thinking about, okay, what makes sense in terms of the coefficient of performance, because in this case, we reversed our reservoir. So you can reuse what we learned about the Carnot efficiency in the previous video. And so you have these relationships now between the work that's being done and the temperatures. And your coefficient of performance in this case is given by the ratio of the heat that is going into the hot reservoir. All right, so that's what we want to maximize, divided by the amount of work that's done to be able to perform that. So it's just to keep in mind that if you look at this, we use the same elements. A lot of the time we just switch arrows and we label things a little bit different based on what is the uh, the element that's supposed to receive heat or lose the heat. And but all throughout these processes, we keep in mind that our energy is conserved, and that if you're performing work, or you're using the work to be able to generate the processes that are needed. We have to look at the whole cycle and make sure that where it's all doing what it's supposed to do, and we keep track of where the energy is going and where it's coming from. All right. So maybe next time you look at your refrigerator, you look at it a little bit differently. But you can notice that there is an exhaust, and typically the back of your fridge is going to be warm. All right. Okay, so really quick, in the next video, we'll talk about the third law of thermodynamics, and then we'll talk about more considerations about the processes, what happens, when you actually bring heat to a system to either change its temperature or change its state, which are things that we saw when we looked at the engines. All right, bye.